Welcome everyone for today's Quantum Space Time seminar. Today we are very happy to have Jay Gurjali from Penn State University and Niels Bohr Institute, and he's going to tell us about adventures perturbation theory. Over to you, Jay.
Well, thank you very much for this opportunity. It's good to see old friends, even virtually. And my talk today is really in kind of two parts. Part of it is phenomenological about about a question that seems to not have been asked very often, or at least not with much progress over the years, which is just what is the class of mathematical functions that come out of perturbation theory, the kinds of numbers. This has been of interest to number theorists. And then what some of the things we've learned recently and ways in which we've gone about recent improvements to our general toolbox to probing the structure of perturbation theory and general quantum field theories, but beyond especially one loop, which turns out to be relatively simple. But I want to start by stepping back and asking a very simple question, which is what is the mathematical form of the predictions made in quantum field theory, especially perturbatively? And this is as somebody who works in this field, I can tell you they're surprisingly sparse. There are very few observables or observable-like quantities, even toy models that have been computed to even modestly high order. And the ones that have gone the farthest are those of the most important experimental values, or the ones that are, that have been really pushed by integrability or other things like that. And most of the examples are in the class of specific numbers. Take, for example, G minus, or the gyromagnetic ratio of the electron, which we all know from undergrad, I guess. So at tree level, we have 2. And at one loop, we have our students calculate this, usually over a homework assignment over a week. It's a bunch of numerator algebra, a couple pages of numerator algebra. If you're a good professor, you can usually get it done in a lecture. And when all the dust settles, you find the number 1, which is a little embarrassing, and I think it should embarrass us more. At 2 loops, this becomes a research level problem, first done by Peterman numerically, Sommerfeld analytically. And of course, if you're an experimentalist, if you care about matching to experiment, this should suffice, which is higher precision than Peterman had, of course. But Sommerfeld gave this expression, which I think, is at least interests me more. You can see that the numbers are zeta is the tri-logarithm evaluated at the number 1, zeta 3. We have a pi squared, we have log 2, so logs and zeta values are pretty common. And we have some rational numbers. This is just phenomenologically. What about higher loop? Well, this is a difficult enough problem that this required supercomputers and wasn't completed until the 1990s by Kinoshita. Numerically, you get an approximation like this. I think Kinoshita had a few digits. And more recently, Laporta had pushed this analytically to infinite precision. And the weirdest number that arises here, so we have zeta values, which are, again, polylogs evaluated at the number 1. We have log 2 making an appearance, and this U31 is some complicated thing, but the weirdest number that appears in it is the 4th classical polylogarithm evaluated at 1/2. And if you've looked into this, you might have noticed that Laporta very recently pushed this to 4 loops, but not to infinite precision like this, but to, in some cases, for some contributions, to tens of thousands of digits. And the reason why he pushed it to tens of thousands of digits is because it turns out that an expression like this to infinite precision does not exist and cannot exist at 4 loops. And I'll give you a small hint at why. The reason is because there are non-polylogarithmic contributions. Starting at 4 loops, you have Calabi-Yau periods that make an appearance. And these things don't have names yet. They can be computed to tens of thousands of digits, but they are numbers that aren't named yet. They're not in a database. So Mathematica doesn't know how to get digits out of them. And generally speaking, we don't know how to do them. So there's already a hint that the class of numbers if I was giving a more exhaustive survey of this, I would have pointed out that, or something to point out is that Kontsevich had even formally conjectured that all Feynman integrals, at least ones that didn't have any kinematics in them, would be zeta values. This was well before these kinds of analytic expressions were known, and for a long time it seemed like Kontsevich would be correct until about 2011, when the first counterexamples were shown in phi-4 theory. So we now know that this is an interesting class of numbers that come out of quantum field theory. But whether you want to say that these are nice numbers or ugly numbers, I don't know. I am not a number theorist, and I'm not really sure to say. But I think most of us, at least, in this seminar, would agree that an expression like this, which is to infinite precision, is preferential to some numeric expansion. At least it starts to expose the kinds of structures that we might expect at higher orders in general. What about nicer quantum field theories? I mean, QED is massive, and it's not even the full standard model, which we could discover by discrepancy at experiment already at 5 loops. But I think that most people studying amplitudes consider this our favorite theory, maximally supersymmetric Yang-Mills theory. And in this case, there's one observable or observable-like quantity, which has been computed to essentially arbitrary precision, perturbatively, using integrability, so not using Feynman diagrams or anything. And you'll notice that these are very nice numbers. In fact, it's generally true to all orders of perturbation theory that you can write the cusp anomalous dimension. This is for 2 to 2 scattering. I should make this an alternating series for the experts in the audience. It's a mistake, but you can always write it as integers with zeta products of zeta values, classical zeta values to all orders of perturbation. So this led to the idea that perhaps the nicest quantum field theories would be those ones that would be, oh, and also you'll notice that the weights of these things. So if you assign a weight of 1 to pi, and zeta 2 is pi squared over 6, zeta 4 is pi to the 4th over 90. So if you give a weight to the zeta values, you'll notice that everything at this order is weight 10, zeta 2 to the 5th, zeta 3 times zeta 7. So there's a notion of saturating this transcendental weight. This saturation happens kind of on general grounds. If you have a d-dimensional Feynman integral at L loops, there's the volume part of the integral always gives you d over 2, the ceiling of d over 2 transcendentality, pi to the ceiling d over 2. And so whatever the rest, the non-trivial part, the non-spherical coordinate part of the Feynman integral is going to give you is going to be some number which has a bounded transcendental weight of the floor of d over 2. And this led to this idea that at least planar n equals 4 might be the nicest theory, the one that saturates this transcendentality, and that everything would be exactly this weight. And of course, today this statement has some questions, but I do think that first, I do think this calculation is correct, and also I do think that there is a notion in which n equals 4 is maximally transcendental. But we will see that the notion of what transcendentality means, and also the notion of saturation is also a little bit more subtle. So with a suitably redefined or suitably expanded notion of what transcendentality means, perhaps. But beyond the case of single numbers, it's hard to say whether or not a number is simple or not. These are clearly simple. These are pretty nice numbers. But to really get a sense of the kind of simplicity that we've discovered, that has been discovered in the space of these observables, I want to change our attention to, scattering amplitudes, functions of many variables, of all of the on-shell particles and all the on-shell descriptors of all the physical states. And of course, those things are much broader, more complicated class of functions. They depend on many variables. They have to satisfy constraints like momentum conservation, that they're on shell, gauge invariant, etc. And unfortunately, these are just extremely difficult to do, which is not necessarily a sense that you get from taking a course in quantum field theory. But of course, beyond the most the questions that are, or the examples that are described in most quantum field theory textbooks, I think it's safe to say that beyond the most trivial scattering amplitudes, those involving the very fewest numbers of particles and at the very lowest orders of perturbation, the Feynman expansion, the tools that we teach our students still today, render all but these most trivial observables either intractable computationally or just utterly theoretically inscrutable. And there's an example of this, and as the card-carrying amplitudologist, I feel obliged to tell the story, although I'm sure it's a bit, it's the one that everybody knows very well. But of course, you know, this is a shame that these, yeah.
So, Jacob,
yeah.
one question, if I may.
Yeah, please.
So, let's say, you know, one kind of understands the form of the transcendental numbers that are that should appear, that would appear in the in this either the Kasparov's dimension or this magnetic moment. Is there a sense in which the coefficients can be fixed by some simpler computation?
The coefficients. Yeah. So
the expectation is that there should be rational number multiplying each of these numbers.
Yes. Yeah. So there should be weight zero numbers in front. In this case, I'm not sure any way to calculate this other than getting the full answer. And it's not actually very unique in the sense that, you know, zeta 4 is pi to the 4th over 90, zeta 2 is pi squared over 6. So these are really just ways of shuffling around pi's. All the even zeta values can be mixed up and you can combine them as just a coefficient of pi to the, in this case, pi to the 10th. I think this is very suggestive, but you'll notice like Lance Dixon would never write this formula because it's, you know, it's pi to the 10th is the number, and then you'd write it with that rational number. I think it's very suggestive that you can write it as integers times these numbers. When we get to functions, the coefficients of the transcendental pieces are in general what we call on-shell functions and can be computed independently of the transcendental parts. But I'm not sure in this case, because I don't know an on-shell way of calculating this other than just directly doing the Feynman integrals, which is too hard to get to this loop order.
Thank you.
Yeah, that's a very good question. Yeah. But even at tree level, where we don't have any transcendentality, everything is rational. We know it's just a sum of a bunch of Feynman diagrams, which are individually just rational functions, with a suitably easy Lagrangian. Like as soon as you get past a quantum field theory textbook homework assignment, it's just and that's not just a research problem, it becomes completely intractable. And to give you an idea of this and to appreciate how salient these problems were, I mean, you can consider something like two gluons collide and create 4 jets, you know, 2 to 4 process at the LHC, which happens millions of times a second. This was once viewed as hopeless, computationally intractable in the literal sense. There was a paper in 1984 outlining the theoretical challenges, not the plenty of experimental challenges, but the theoretical challenges to be faced by the then planned or envisioned superconducting super collider. And in it, they outlined that one of the challenges was that the background calculations for 2 to 4 have not been calculated, and their complexity is such that they might not be evaluated in the foreseeable future. And so then they asked, you know, it's worthwhile to seek estimates for these cross sections, even restricted regimes. Why is it hopeless? Well, if you open up a textbook and follow your nose, you find that 2 to 4 gluons, even in just pure Yang mills without any quarks or anything like that, 220 Feynman diagrams. Each one of these vertices is an explosion of terms, and you have to square the whole thing. So we're talking about millions of terms in the cross section. This is something you'll never do on pen and paper. And in the early 80s, it seemed completely out of reach of even the best computers people had available. But, you know, a challenge like this, and also the experimental importance of having these kinds of predictions to discover new particles, say, drove a couple of physicists at Fermilab, Park and Taylor, to put their backs into it. And they threw everything at it they possibly could. They introduced an auxiliary supersymmetry. In hindsight, it didn't help them very much, but they used supersymmetry. They used the world's most powerful supercomputers. They added up all the terms, and the final answer they got was a short 8 pages. And I know you can't read this, but these pages are just matrices of coefficients and one big formula. This is the whole paper. There's a introduction and a small conclusion, but basically the entire paper is one formula. But the reason why I absolutely love this story is because of at the end, after apologizing for not giving any details of the calculation, like we never do, they ended on this kind of weirdly optimistic note that furthermore, we hope to obtain a simple analytic expression for the answer, making our result not only an experimentalist, but also a theorist's delight.
I have a question here.
Yeah.
So, does this include only tree diagrams or loop diagrams as well?
Only tree.
Why not loop diagrams?
They couldn't do it. It was just too hard. Already at tree level, we're talking about hundreds of diagrams, thousands of terms before you square it. It just seemed hopeless.
Yeah, but then how are you assured that it will lead to the correct answer?
That's a good question. Now that we are a lot better at doing these calculations, we know that the tree level results are not very reliable. In particular, there's another aspect of this story that I don't think that is salient for students of quantum field theory, is a process like this where you have 2 to 4 has many scales in it. It's not at all clear where you're supposed to evaluate the renormalized coupling at in a multi-scale process. And what theorists do now when you try to test, when you confront theory and experiment at the LHC, is to literally run the coupling constant from the smallest scale to the highest scale and write a theoretical error bar from that. That's morally corrupt. And it's something that is only justifiable if you have a lot of orders of perturbation theory beyond you. And what we know now is that typically for the LHC, say, when you have many scales in the problem, the theoretical error bars at tree level are enormous. And they only start getting small when you get to pretty high loop order. So at tree level to 1 loop is usually a 30% effect. And then from 1 loop to 2 loop is another, order 1 fraction. So I don't know how you would trust these predictions to be very reliable at tree level. But at the time, we're theorists, we calculate stuff. I don't know. Yeah. It's a very good question. But I also want to treat this kind of phenomenologically. The point is that we have this toolbox, we have this black box called quantum field theory that spits out predictions for things like this. And maybe we have to go to higher order. It might be really hard to get to the next level of the prediction, but in principle, we have a standard answer. And I just want to know what those things look like. Well, within 6 months, they had stumbled upon a guess, which they checked numerically matched this 8-page formula. They did not derive this, but it must have exceeded their wildest dreams, because that entire 8-page formula reduced to a single line in the spinor variables that were introduced quite a long time ago, although they didn't use this notation. But much more importantly than this 2 to 4 process example is that it naturally suggests an analogous 1-term formula for 2 particles in to any number of particles out. For the experts in the audience, all the same helicity. And when they had this guess, they checked that it worked for 2 to 2 and 2 to 3 and 2 to 4, which they had on their computer. And naturally, they conjectured it to all multiplicity. And if this formula doesn't, impress you, or I don't know, I think this needs to be viewed as an indictment on the tools that we use in quantum field theory. Take, for example, when two particles create 50, the number of Feynman diagrams, not number of terms, which is not gauge invariant, but the number of just graphs that you have to add up in Yang-Mills without quarks at tree level exceeds the number of atoms in the universe. It's 10 to the 84, I think, for 2 to 50. And here's Park and Taylor telling you that if you added up all of those terms, that you would just, they would all cancel each other out and just leave you with this simple expression. This is a sign that we're not understanding something, that somehow the Feynman expansion, although correct, is somehow deeply obscuring some underlying simplicity. And much of the revolution in amplitudes in the last 20, 30 years has been understanding why this guess is correct and systematizing ways in which we can understand why things like this kind of beauty can be understood and used, exploited into powerful technology to push things further. And I think broadly speaking, the goal of the Amplitudes program is to make this simplicity, this kind of thing, not surprising to us, to both, not only to understand it, but to build it into a better framework for making predictions that allows us to answer a lot more questions. But what have we learned about this particular process beyond the leading order? And here I'm actually going to transition to n equals 4, just because that's where we understand it the best. In the case of pure glue, this has really only been calculated numerically at one loop. Analytically, it's only known to, I think, 6 particles. But we can talk about this in planar n equals 4, which matches pure Yang-Mills at tree level. And there's a lot of surprising structure. And the first part of the story that I'm going to come back to in the second half of this talk is that it turns out to be a really good idea to separate the difficult problem of doing Feynman integrals from the relatively easier problem, although still very hard, of adding up all the Feynman diagrams, namely talking about the integrand, which is the gauge invariant sum of all of the Feynman diagrams you have, which is a d times L differential form on the space of loop momenta, and doing the integrals. Anyway, one loop, it was shown by Byrne, Dixon, Dunbar, and Kossauer that the whole thing was the sum of little box integrals like this. The wavy line you can forget about it. It's just some particular tensor numerator on loop momenta, but can be written in terms of the Feynman integrals with 4 propagators with 2 massless legs in the corners. Well, what about 2 loops? Well, when you realize that the Feynman, the loop integrand is a differential form, you can expand it into an arbitrary basis of differential forms. There's a cohomology there. But like everything with a cohomology, or anytime you need a basis in math or physics, your choice of basis matters a lot. But in principle, the Byrne, Dixon, Dunbar, and Kossauer told us how to determine the loop integrand by picking a basis and just solving a linear algebra problem. And this was done first by Christian Vergu, to all multiplicity, first by Christian Vergu in 2009. Pretty heroic calculation, where he chose a basis and and solved the linear algebra problem and wrote down the general endpoint generalization of Park-Taylor's guess, and it spanned a mere 12 pages. And of course, you know where I'm going with this. Within 6 months of this paper, pretty independently, I would say, my collaborators and I had stumbled upon a different formalism for calculating the right answer, and it allowed us to guess and check a much more compact expression, which we've had for a while. And in fact, we were able to push this to 3 loops, and much more recently to more or less any quantum field theory at any loop order. There's a very systematic way of writing down a complete basis and determining all the coefficients in that basis in terms of on-shell physical data, which I'm going to come back to later on. But these are, of course, just integrands, and you have to do the integrals. When you do the integrals, the first obstruction, of course, is that the S matrix beyond tree level is not really, well, even at tree level, but you have to, you're forced to encounter it and to deal with it at loop level, that the S matrix is not an observable.
Sorry, is your basis planar in any way, or?
Yes, this is in planar maximum supersymmetry, but we now know how to do this
okay,
beyond
sorry.
planar.
Yeah,
we now know how to do it in a general case. Yeah, that's a good question.
Of this, of this space?
Say again?
What is the dimensionality of this space of forms?
This is 4 dimensions.
The dimension. of
Of
this
the integral
forms?
basis.
Yeah, integral basis. Yeah.
That's a very good question. I think it's an open question. This is a basis large enough to include this answer, and we have I know the answer. I know an answer to that, which is sufficient through about 7 loops, but I know it is too big, so I don't know. It is an interesting problem that is completely open, I would say, to determine the smallest basis, or what is the subspace in the space of Feynman integrams that contains amplitudes in n equals in maximum supersymmetry. In the planar limit, people would say a standard answer would be the space of dual conformally invariant integrals, which is a very strong restriction on the space. But we already know that that's way too big. But beyond the planar limit, nobody even has a definition that includes dual conformal invariance at arbitrary loop order. So this is a wide open question. If you're interested in non-supersymmetric theories, there's a very kind of cool graph theoretic answer for a basis that's large enough to include the standard model at any loop order. Basically, anywhere normalizable perturbative quantum field theory in any number of dimensions lives in a finite dimensional basis that you can just write down. So that's kind of the biggest class of integrals. But n equals 4 uses very few of them, and a very small slice of this, and I don't know the size. So.
Sorry, what is this basis you're talking about? What is this basis you're talking about?
Yeah, I'm going to come back to that in the second half. So, but it's a good question even now, which is just what is the class? You know, I mentioned that the sum of Feynman diagrams is a representative of cohomology. So you might want to know what is the dimension of the cohomology that's relevant for this quantum field theory. It's definitely a finite dimensional space. How big is it? I'm going to spend a lot of time talking about bases and choosing good bases in a bit. But of course, you know, we want to do the integrals. And the first problem is that doing the integrals, these are all infrared divergent. The S matrix is not an observable in a massless quantum field theory. And that means that there's a whole nother level of complication, which is that to construct a finite observable, or observable-like quantity, as some people might call them, like, well, the ratio function, which is the ratio of 2 different amplitudes with fixed helicity configurations, say, or fixed color content, the ratio of these 2 things is infrared and UV finite in any quantum field theory. It's a nice observable, but in terms of amplitudes, it's constructed out of amplitudes, out of building blocks. A much more familiar one is the cross section, which of course involves mixing tree level and one loop, or lower loop, real emission from lower loop, and infrared divergent integrals at higher loop. These are these are complicated, and in fact they're so complicated that beyond one loop, I don't think anybody had a single 2-loop finite observable prediction done to infinite precision. I mean, in terms of an analytic expression we could manipulate or understand until 2010, where this 2 to 4 process in planar maximum supersymmetry was computed. Well, it's divergent, but its divergence is fully controlled by this cusp anomalous dimension, and there's this finite remainder function that you can calculate. And this was first calculated in this truly heroic paper by Smirnov, Del Duca, and Durer, where the paper is about 120 pages, and 18 of those pages are an appendix where they just give the formula. So but this is the first 2-loop observable in any 4-dimensional quantum field theory. And it involved regulating things and combining them and canceling out all of the regulator dependence. This was a heroic nightmare calculation, and you know where it's going. Yeah.
In the expression, in the expansion you had 2 pages ago. Was that in 4 dimensions or 4 minus epsilon dimensions?
So these expressions are in 4 dimensions. So this is not consistent with a dimensional regularization, but in a theory like n equals 4, where you only have infrared problems, you can use a mass regulator, so they're fine. I mean, they're still usable for calculating finite quantities, because all the infrared divergences will be regulated with masses. In strictly speaking, the dimensionally regulated integrands are slightly different than these. You can do the same game, you can play the same game in 4 minus 2 epsilon dimensions, but then you need to be very clear about what your dim-reg conventions for the internal polarizations are, what scheme you're using. So there's a lot of options there.
That has been worked out. This a similar expansion in 4 minus 2 epsilon has been. Okay, thank you.
Yeah, these people used the 4 minus 2 epsilon dimension, which is what, when Christian Vergu wrote down this formula, it was in dim-reg. So this was valid in 4 minus 2 epsilon, and they just regulated everything in dim-reg, and they got this 18-page formula. This, you can't see it, I know, but if you could, you'd see that inside here are a bunch of G's, which I'll come to in the next slide. But these were described in the first 100 pages of this paper as Goncharov polylogarithm. And Christian and two collaborators, Anastasia Volovich and Mark Spradlin at Brown at the time, or at Brown, wanted to play with this. They had an attachment to, as a Mathematica file, but Mathematica doesn't know what a Goncharov polylogarithm is either. So they Googled it and found out that Goncharov was a mathematician just down the street at Brown. So they went and visited him and asked him to explain his polylogs. And he, like any respectable mathematician, refused to look at an 18-page formula like this. But he told them to go home and compute something called the symbol. They did. The symbol was one line. That got him excited. And within 6 months, they found that that entire 18-page formula can be written in terms of classical polylogarithms, not the fancy Goncharov variety, in very compactly. Now, this is this kind of obviously it's a recurring theme in this talk, but it's a recurring theme in this subfield where somebody pushes something very hard by whatever means you can possibly, use at your disposal, calculate something new, and then sometimes the same people, sometimes different people discover something amazingly simple, and then you scratch your head and you spend some time thinking about it. And once you understand why there's something so simple, you can push it to expand into more powerful technology to go further. And to get and appreciate this, that, since in the last 15 years since this paper came out, Lance Dixon and collaborators, mostly Lance Dixon and his collaborators, have pushed this particular 2 to 4 process to 8-loop order, is the state of the art. 2022 is the most recent date. And 7 points, 8 loops, or 8 points have been pushed to very high loop order. And they've really, yeah.
The previous formula that you showed, the U1, U2, U3 were some Mandelstam variables?
Yeah, so in this case, the function is known on general, well, this ratio remainder function is known to be a function of 3 conformally invariant cross ratios. So they're cyclically related to each other. So U1 through 3. These x's involve, it's not actually rational in the U's. It has an algebraic field extension of degree 2. So there's a 1 square root in the U's that's kind of annoying. It's like a Gramian. So the xi plus and minus refer to that. It is rational in twistor variables, but that's not the way they wrote it when they first wrote it. Choosing the right variables so that things are algebraically simpler is also a very interesting thing to think about. But at this point, so this is, by far I
have another question.
Yes.
Like when you're talking about doing this calculating these to infinite precision, what is the point? Because at the next loop order, they will be altered in any case, right?
Mm-hmm. Well, so this is a great question. And I think, it's like the decimal expansion versus writing it as log 2. As a theorist, I certainly understand log 2 better than I understand the decimal expansion. Or rather, decimal expansion doesn't really help me understand the functions very well. So there are different standards by which you could say you got the calculation, you made the prediction. In n equals 4, there's no experimentalists interested in these predictions. So it's really just for theorists by theorists. And, there is value in a numerical data point, But when you see a formula like this, it makes you think about the class of functions. We understand this class of functions extremely well. We know their branch cut structure. We know we know how they are analytically continued. This is a class of functions that we understand very well, and writing it this way, more important than getting a million digits out of it, because I don't know if I care. It's nice that Mathematica can get a million digits out of polylogs, but much more important, I think, is that it exposes the branch cut structure, all of the physically interesting structure that we might care about here. And that is something that is largely open. So on the topic of polylogs, you might expect, through pretty much every example we've seen now, except for some hints, that polylogs are the right answer. Everything that we've been able to calculate, basically, virtually every example that has ever been calculated, that has been understood and written down, is a polylog. And I think that's a little bit lampposty in the sense that these are also the only ones we know how to do. And as soon as you get outside of this class, they're usually thrown in a bin called "we don't understand them" or "we can't do them." But nevertheless, it is a general statement that at one loop, in any number of dimensions in any quantum field theory, just a general one loop Feynman integral is expressible in a polylogarithm here of weight, which is the number of iterations on this integral of ceiling d over 2, or d minus 2 epsilon, if you want to do that, if you want to use Dimrag. But this is a very general statement. They're not always classical polylogarithms. It turns out that the space of these Goncharov polylogarithms only is much broader and includes what are sometimes called hyperlogarithms and harmonic polylogarithms. They're all special cases of this broader class. But the ones that Euler wrote down is a much more narrow class of these things here. So it turns out that many amplitudes at higher loops, and especially at low multiplicity, and these examples like Lance has pushed, I'm pretty sure those are polylogs to all orders. It could be that MHV amplitudes are polylogs at all orders. I'm not sure. It seems plausible. Sir, I think Lance isn't missing anything, and certainly the Cuspin-Amos mentioned, I'm pretty confident that's correct too. But outside of this very narrow category of few particles or restricted helicities or very low loop order, this is not a big enough class. And we're really just learning the space of functions that do arise. The good news is that it's not quite as big as you might think, or at least we haven't found a very big space. So broadly speaking, what do we expect these functions to be? If we look at the loop expansion in a d-dimensional theory, we'd have this d times L dimensional Feynman integral to do. And like I mentioned, there's a volume factor that has weight of a ceiling d over 2. So you'd expect that these things here have a certain transcendental weight, whatever that means. And indeed, in 4 dimensions, say anything you calculate at loop level, at one loop, starts in generic, it's weight 2 polylogs or pi squareds. Weight 1 polylogs are just logs, and rational functions. So we have this kind of tower of transcendental weight. And you'd expect that basically at 2 loops, at least in maybe a nice quantum field theory, you'd have weight 4 polylogs, et cetera. And this indeed is, this expectation is met by every calculation that anybody's ever been able to do until very recently. The coefficients of these integrals in general have weight 0. They're like the rational numbers that was asked about earlier. They're on shell, they're gauge invariant quantities. They have interesting cut structure, etc. And I used to say that they would be algebraic functions of the Mandelstams and stuff. But that is not true. There are counterexamples. That's not true. But they are weight 0 in an appropriate sense. It's just that they might be weight 0 in a much more interesting sense. And that's a story for another talk, I think, another day. but broadly, but in general, they are leading singularities, meaning that the coefficients of all these polylogs are determinable in terms of on-shell physical data without any gauge invariant redundancies or the Feynman expansion in general. So we understand the coefficient space very well. That was most of my graduate school, research and, early career. And we're only just starting to understand the polylog or the transcendental functions that arise. That's mostly the focus of this talk.
So
but n equals 4,
is the understanding that since you have just polylogs and logs, there are no divergences? Is that the understanding?
Well, I would say the divergences also fall into this category. If you assign epsilon a weight of -1, then it fits into this structure just as easily. Or I would encourage you not to look at a regulated expression and look at a finite observable, in which case there's no epsilons, and then this is the expectation for, instead of A for an amplitude, you can just say any observable.
So is there a big difference between planar theories and general theories, or this subsumes everything? Could be that planar theories are much simpler, the number of dots grows polynomially and not combinatorially, etc.
That's a great question. The main distinction that I'm aware of is that the distance from this expectation of polylogarithmicity, it's much more severe for non-planar than for planar. But that's about it. So the exceptions to this rule of polylogs arises much more quickly for non-planar theories. But otherwise, it's the same class of functions, the same weight bounds. The bounds and the weights just have to do with the number of Feynman integrals you have to do. But what you mean by weight, so when I say a weight for polylog, mathematicians would not object to what I mean. Although if you really get down into the details about what weight means for these zeta values, we're talking about the Hodge conjecture and some subtleties about the standard conjectures that are just, that they're half conjectural, some things you can prove based on the standard conjecture. Some of them are just generally conjectural, but we don't have to deal with any of those open problems in mathematics when we talk about polylogs, or at least in this particular category, in the sense that there's a well-defined notion of weight. These things exist. But as soon as we start finding exceptions to these polylogs, it starts getting into uncharted territory in mathematics about what do we mean by weight. I'll come back to what I think the right definition of weight is. So this, I think that if you would have polled people as recently as, say, 10 years ago, the experts in the field, that they would have expected that the maximum transcendentality of n equals 4 meant that it lived in this nice slice at all loops orders, and that we would expect these polylogs of some given weight, which would have been very convenient because polylogs happen to be a class of functions, of special functions that we understand incredibly well today. We understand their structure, how to write them in bases, all sorts of things. Unfortunately, this isn't true. And the first counterexamples started to arise, in a few different places. It's a little hard to get the history and the appreciation of how much these mattered to real experiments or real theories that you cared about. But probably the easiest example that everybody should know is the sunrise at 2 loops. So this is a massive integral with 3 masses. It's divergent in 4 dimensions, but in 2D, it's finite. And it's very easy to see from several different ways of calculating this, that this is an elliptic logarithm. It's not a polylog. It's an elliptic integral. And more recently, we've understood this whole series that at 3 loops, you have general masses inside here, you have a K3, the volume integral of some K3, some Clabeyao threefold at 4 loops, etc. And there's a great work by Chuck Doran and collaborators where they showed this whole class. These are all elliptically fibered Clabeyaos with a very nice mirror symmetry properties, and this is a very well understood class, and it's and their elliptic vibrations are one of the reasons why we can calculate these periods very well, or these Feynman integrals so well. And in particular, this one, this Calabi-Yau threefold, appears in the electron G-2 calculation at 4 loops. So this unknown number that Laporta couldn't find in his database, and he didn't know it was a Calabi-Yau, but he called it a multiply elliptic integral, which he calculated tens of thousands of digits. Doesn't have a name, but it is the volume of some particular cycle, some middle dimensional or real form on this Calabi-Yau three form on a Calabi-Yau threefold. Anyway,
Calabi-Yau threefold.
What?
On some particular Calabi-Yau threefold.
On a very particular Calabi-Yau threefold, yeah. Given by the quintic, where the coefficients of the quintic are the masses that appear here. So it's a very special, turns out to be also very singular Calabi-Yau threefold. Beyond, maybe you'd hope that massless theories will behave better. And indeed, Kontsevich had this conjecture that at least, where masses don't matter. So in the case where there's no kinematic data at all, so he was interested in vacuum graphs, essentially, that everything would be polylogs. Well, the first counterexample appears at 8 loops from this graph here, which is known to involve a K3 by Brown and Schnetz. And it's interesting, recently Schnetz put out the 7-loop analytic form of the cusp anomalous dimension, or not the cusp anomalous dimension, sorry, the cusp, the gamma for the coupling constant in 5-4 theory, and to infinite precision, with zeta values. And the weird numbers that appear are all polylogs, like zeta 3, 7, and stuff like that. But at 8 loops, we have this problem that there are numbers that we don't have names anymore. So nobody has an analytic expression, even though we can probably calculate this at 8 loops to, thousands of digits. Nobody knows the names of those numbers that appear. But it's surprising to me that the mathematicians, especially these graph theorists, number theorists, were looking so deep in perturbation theory for these counterexamples, because they start arising in 5-4 theory much easier, much more quickly if you look at functions. So this stands for a massive corner, which could just be a pair of massless legs in massless 5-4 theory. This at 2 loops is an elliptic trilogarithm. And in fact, at higher loops, it's the same story. So there's an elliptic curve is a Calabi-Yau one-fold. So we have a Calabi-Yau one-fold, and we have a K3 at 3 loops, a Calabi-Yau threefold at 4 loops, etc. And all of these are defined in massless 5-4 theory. And if you want to be more provocative about it, these Feynman integrals here are exactly the same as the position space tree level amplitude for, in this case, 6 particle scattering. So the tree amplitude for 6 particle scattering in 5-4 theory in position space is a elliptic trilogarithm that amazingly hadn't been calculated until quite recently. But once we started looking for counterexamples, we found them all over the place. So in particular, and beyond the planar limit, we constructed a series of examples. This is at 8 particles. So at 8 particles, non-planar 2 loops, you have a K3. And this, unlike the train track series where you have to add new legs at each order to get to flesh out the counterexample. If one of these legs were absent, you'd go down a loop. So this would become this Calabi-Yau threefold would then become a line times a K3. But for 8 particles in 5-4 theory, there's no notion of planarity in 5-4 theory, these counterexamples persist to all orders. So we call this the distance from polylogarithmicity, the rigidity of these examples. And so basically it's the smallest dimension over which you can't write it as a polylog, as a D-log form. And because every Feynman integral is in 4 dimensions, every Feynman integral is a dialog. Every 1 loop integral is a dialog. That means that the most you can ever expect for your non-polylogarithmic part would be the weight, which is 2d, or two times the number of loops minus 2. So this is the highest rigidity you could expect, and indeed it's saturated. So we could find examples that have the farthest from polyalgorithmicity you could imagine at fixed multiplicity to all orders of perturbation theory. So this is a more complicated, more interesting example. And I think it's safe to say that now that for reasons that, well, that I'll get back to soon about integrand bases, it is now widely expected essentially that all observables, or that essentially there's a set of measure zero of observables that are expected to be polylogs. And outside of that class, basically almost all observables and almost all QFTs are expected to be non-polylogarithmic. Now, this might scare you. It scares me, but there's hope. And it's not just because Calabi-Yaos happen to be a space of, geometries that physicists happen to know very well, but it's also because the class of the Calabi-Yaos that we see are extraordinarily simple. In fact, in every single example we've seen, Calabi-Yao itself is just a degree d+1 hypersurface in PD. It's the quintic for the Calabi-Yao threefolds. These are there's the chapter 1 of any book on Calabi-Yao geometry for string theorists talks about the quintic. These are the easiest ones to talk about. But unfortunately, the role that Calabi-Yaos have played in physics so far have been mostly about general structure, about their Betti numbers and things like that have been used, but the actual doing the volume of these particularly singular Calabi-Yaos whose moduli, complex structure moduli, depend on kinematics, hasn't been something that has been studied very far. There are very few examples of Calabi-Yao periods that have been computed well, and they're usually in especially simple or nice, mirror symmetry. Mirror symmetry is usually used to write down the Picard-Fuchs equations and to compute these things. But this is uncharted territory. We start encountering very quickly functions that we just don't understand, we don't have names for, and we don't have general tools to do this. I'm leaving it as an open question for you going forward. But I want to address, yeah.
Calabi-Yaos, I was wondering if there is a more geometric way of understanding the emergence of these Calabi-Yaos. I guess they come out of integrand. Yeah, sorry, go ahead.
It's a great question, and it's one I've thought a lot about. But as far as I can tell, the metric structure on these things doesn't seem to matter very much. Or it doesn't seem to. That's not why they're Calabi-Yaos. They're mostly Calabi-Yaos just because the Feynman integral itself turns out to be a holomorphic differential form, a nowhere vanishing holomorphic differential form that is the way to describe these. The Feynman integrals just happen to be that. So you end up getting the DD form on these things, and it just happens to be a nice volume form. So I don't really know the Calabi-Yao geometry isn't playing a big role. I don't know. It's for different reasons than in string theory. It's just kind of a general property of these integrals, Feynman integrals.
These unitarity cuts also can be written in some geometric, can be understood in some geometric way on this. Not in the sense of metric, but from the point of Calabi-Yao directly.
Yeah, so there's a lot of geometry intuition that informs the structure of these functions. And I already alluded to some of it here. In this case, this series is kind of trivial. It's more interesting here, where you can go to hypersurfaces. So you can go and, if you have maybe an easy example is this elliptic integral. You can go to a point, you can move the kinematics in a plate into a place, a configuration where because the kinematics are screwing around with the moduli of these Calabi-Yaos, you can go to a space where it pinches, for example, and then it becomes a polylog again. And similarly here, like you have a K3, but you can bring it to a configuration where it becomes a product of elliptic integrals. or elliptic geometry. So as you move around in kinematic space, you're moving in the moduli space of these claviaus, and the functional structure that you find reflects the geometric structure. In general, it's not a product manifold, but you can find plenty of spaces in code hypersurfaces in kinematic space where this thing factorizes into a claviao twofold and a onefold, say. But other than that,
it could be that the appearance of higher dimensional, you have this higher dimensional claviaos appearing, which would have a huge modular space, let's say, dimensional model. The dimension of the modular space could be huge, but if there is a mapping of the Mandelstam space into it, then that is just exploring some particular slice of it. Then what is the significance of the rest of it and so on? Does it matter for a higher point functions and things like that? I guess one could ask, and it's probably along with that.
Well, you could, yeah, that's a great question. I'm not sure the right answer. I mean, if you have a fixed multiplicity, so you have a fixed kinematic space that you care about, I think it's safe to say that you could embed all the Feynman integrals into the moduli space of some, saturated, rigid, some high dimensional claviao, and everything would be an instance of that with some, factorizations or singularizations. That's interesting. I think it scares people a lot because most of the time people spend a lot, say at 2 loops in planar n equals 4, there's basically this one counterexample that you need to deal with, and then everything else is polylogs, and everybody tries to avoid the polylogs as much as they can. But you're right, I think you could embed everything inside the elliptic integrals if you'd like, and then view everything as specializations thereof. So there might be some sort of master claviao geometry that it describes everything. But it's also moving in the scary space. It's a space that people don't understand as well. That's very good.
Can I ask what is probably a very stupid question? The momenta that you are doing your integrals over, are those coordinates on the whatever half-dimensional form on the claviao that you're doing your integral over?
Yes, yeah. So you can describe this in a few different ways. I would say it's an open conjecture that all of these descriptions are the same, but so far they've been the same. But let me just lean on the conjecture and tell you that, I'd be willing to bet 10 to 1 that these geometries are basically identical, or they are exactly the same. They're uniquely characterized by the cut surface of this thing. So you look at the d times L form that you have, the Feynman integral, and you take the residue that puts every propagator on shell, and you get some differential form on the space that's left. That is now, the differential form on the space that's left is some subset of the degrees of freedom of the internal loop momenta. And that thing is the geometry. So the hypersurface is a hypersurface in the space of loop momenta. I set that as a conjecture because in a lot of cases, for example, here, and actually also for this whole series, we did it actually in Feynman parametric space. So we integrated out the L's, on line 1, and then looked at the geometry in Feynman parametric space. And that is usually the analysis that people do. But in every case, here you can do it in either way. You can say, you take a pair of 2-dimensional momenta, you take this constraint that all of them are on shell, you go to a codimension 3 surface, and you find that thing's elliptic curve. And it's the same elliptic curve as you would have gotten in Feynman parametric space. It's the same elliptic curve. That wasn't so clear. There were a few instances where people were confused by that, but it seems to be the case that basically the geometry is unique to the Feynman graph, and it doesn't matter what variables you're using. But yeah, so the form is I think it's safe to say it's just the loop momenta. It's the loop momenta where every propagator is on shell, and divided by the Jacobian of putting everything on shell, and that is the geometry that we care about. So that's the Feynman integral we care about.
Have you tried doing Schwinger parametrization of these things and whether things kind of simplify?
We have. I think in the case of the Sunrise series, this is well understood, but I don't think any of the other examples are very well understood. I mean, there are isolated places where we can do this, but I mean, I don't want to speak for all my collaborators, but at least for myself, I'm not sure if I'm the right person to do that. These are hard. I mean, there are people who know how to do this much better than me. I'm not sure, and I've tried asking most of them, but I don't know. So, no, I mean, it seems now that when we go back in the literature and we see calculations that people did at 2 loops, when they would encounter an integral like this, they just put it in a category of I don't understand it, as opposed to describing it. But I think that now that people, it'd be awesome if somebody who knew more about these Calabi-Yaos got interested in this and could help us do some of these integrals. I'm not sure if I'm the best person equipped for that.
Okay.
Yeah. But it's worth like stepping back a little bit and asking. So moving on a little bit, why did it take so long to find these counterexamples? Why is it so hard to do these? And part of the answer is that the textbook approaches we have to doing perturbation theory are just poorly suited for exposing anything nice. In particular, like the standard textbooks, and maybe this is, it's not against our intuition. In fact, it's exactly in line with our intuition, is that you might start off with 1 over a bunch of Feynman properties, a scalar integral. These are the worst. They're the furthest from nice functional properties. They're terrible geometrically. I'll have more to say about that. But if you open up a textbook on how to do Feynman integrals, you find standard tools like this. And this, for various technical reasons, is still at the core of almost everything that's done at the state of the art in high order, which is like the state of the art is usually 2 or maybe 3 loops for phenomenology things. Everybody uses this, and there's now wide consensus that this basis of integrals is the worst. It has the worst functional properties, but it's so important for some of the technology that it's still an intermediate step, and it's a huge and a costly intermediate step. So part of the reason why it's been so hard to find any of these calculations is because the standard tools that we have to do Feynman integrals are really poorly suited for the kinds of functions that, they're not exposing the functions that we'd like in any nice way. Also, we often don't calculate observables. We calculate regularized quantities that we then build into observables. And the act of regularization itself obscures most of the symmetries that we expect, all the nice properties. In planar n equals 4, for example, we expect the observables to be conformal invariant. Regularization breaks that. What is supermean in 4 minus 2 epsilon dimensions? It really spoils a lot of the nice, structure that we have. And maybe some structure emerges at the end of the day, but it's far from compatible with the niceness of the final answers that we get. And and the fact is that everybody does this in terms of master integrals, so a basis for cohomology, and the bases that everybody uses are just terribly bad. How can we make it easier? And the first is to choose better integrals in the basis, ones that expose the functional properties that we care about, also the physical properties that we care about, like exposing infrared divergences or exposing UV divergences in a simple way. There's a notion of purity, which is the kind of to isolate the transcendental structure in these functions as nicely as you can. And what I mean by purity, this could be more, this is another category of things that is subject to open conjectures in mathematics, but not in this case. What I'm defining is self-consistent, which is that if you have a class of functions, whatever you'd like, if you can grade them or you can filter them according to something that you're going to call weight, and you have the property that the derivative of classes in one of any integral in a given weight class is spanned by functions in a lower weight class, I'll call that pure. And an example of something that's not pure would be like a rational function or an algebraic function times the logarithm of some function. Because when you hit it with a derivative, S is some Mandelstam, when you hit it with derivative, the product rule gives you a log part and then a rational part. So the derivative is not nilpotent in this this space. So it goes from weight 1 to weight 1 plus weight 0, whereas log would be pure. So the pure is like without all the algebraic prefactor stuff in front of it. And this is something we know how to do very well. And to see how incompatible it is with our typical integrals, I mean, this is actually, I think I could probably, it's much easier to write a better example of this, where you would, I mean, but the point is that when you do a 2-loop Feynman integral, what you find is you find horrible algebraic coefficients times beautiful pure functions. And if you were to look at a typical, let's say we put masses everywhere here, in general, you would find that it's a sum of 6 different pure functions with horrible algebraic coefficients. And it just begs you to rewrite this particular Feynman integral with the 1 in the numerator as maybe being a linear combination of nicer Feynman integrals that give you the pure function. At 1 loop, you don't have this problem. And the reason is because everything is at 1 loop is pure up to a prefactor. So, there's no mixture of things. But as soon as you have linear combinations with different prefactors, when you hit it with a derivative, you map back into yourself. It's a big mess. And to make it matters worse, if you looked at, say, this integral, which I think anybody would put in their, well, Smirnov would put in his basis of master integrals with the numerator 1, is the sum of 2 different polylogarithms with different coefficients, plus 4 different elliptic trilogarithms involving different elliptic curves, different subsets of the kinematics here. So this is an example of an integral which is very impure, and it's also mixed weight or mixed rigidity. There's some things that are polylogs and non-polylogs altogether, and it's examples of polylogs that involve different elliptic curves. This is the problem that is being hit right now today in phenomenological applications, where they have integrals where they have multiple elliptic curves. And it's natural to wonder, can you choose a basis of master integrals in which that never happens, where you can write things in terms of pure functions only and no mixture between polylogs and elliptic polylogs? Can you isolate the geometry involved in these transcendental pieces? And can you express your scattering amplitudes in that basis of integrals? And the answer is yes, whenever we can. Another aspect is to avoid regularization whenever we can. What I mean by that is, can you organize your basis of integrals to have all of the divergences in some substrata and all of your infrared and UV divergences separated, so that when you calculate a finite observable, you don't have to do any regularization? And the answer, and so far, every time we've tried doing this, we can construct such bases, meaning that we can organize our calculations such that any finite quantity can be calculated in terms of integrals that are strictly finite, without any regularization needed, without any local divergences. I mean, it seems whimsical to anybody who knows quantum field theory, but to an outsider, I mean, it seems like an absurdly obvious question. Like, why is it that when we calculate a finite observable in some quantum field theory, we expand it into a basis of 1 million terms that are all divergent? Surely we can write surely if we're calculating something finite, we should be able to calculate it in strictly finite terms. A trivial example of that is at, phi-4 theory at 1 loop. If you write things in terms of bubble differences, which is exactly what you're doing for renormalization, you're comparing one scale to another. The difference of 2 bubbles is finite. It's UV finite, and you don't need a regulator to calculate the difference of 2 bubbles. So why not use bubble differences instead of bubbles? Okay, I realize that I'm kind of short on time because I also started late, but basically this is where things are at today. We're spending a lot of time trying to organize the basis of master integrals as efficiently as possible. And one of the things that we've learned is that the bases that a lot of people have preferentially used for their code base, for their, for applications like that you find in textbooks, are really the worst bases. And but as soon as you realize that you're going to expand some expression into a basis of differential forms, it just begs you to find good bases. And it also gives you permission to study a single Feynman integral, independent of the quantum field theory you might think it contributes to, because it's an element of your basis. You can put it in if you'd like, and so it changes your thinking. Instead of calculating some particular amplitude in some particular theory, to can I find Feynman integrals that expose all the physics that I care about? Because if I understand the nicest integrals, the ones that have the nicest analytic structure, I can throw it into a basis. I'm going to skip over this about the ordering of amplitudes, but this is what I was saying earlier. Is it possible to carve up your basis of master integrals? These are the things you need to calculate. It's the basis for cohomology according to transcendental weight. And then within each of these strata, can you further carve it out into polylogs, elliptic logs, K3s, Clabbiat threefolds, etc.? Can you further divide every one of those categories into finite, divergent, by the order of divergence? Can you separate it into UV and IR divergence? And the answer is that every single time we've tried, we can fully carve it up. And in particular, we've shown that at least in planar theories, everything at two loops there exists a basis at two loops where every single integral is a pure polylog or a pure elliptic polylog, depending on a single elliptic curve. So that basis exists. Whether it exists at two loops is actually a much more detailed, interesting question. And part of the problem is that the moduli space for K3 is very large compared to an elliptic curve. I'm going to skip over some of this. But the main lesson that we've learned is that the nicest integrals tend to be the cohomological duals to some cycles in the theory. So the best way to construct a basis, ones that are guaranteed to be pure and nice, is to find a spanning set of cycles, say 4L dimensional or whatever maximum dimensional compact contours. And these things don't need to be residues. They don't need to be related to polylogarithmic things. But elliptic periods, K3 periods, what I mean is just take a maximum cycle. So on a K3, if you have a K3 at two loops, take residues for as much as you can, and then integrate, and then find a compact cycle in the K3 and integrate over it. We can do this in field theory. We can compute those in terms of on-shell data, and in the integrand, we can compute those too. And if we diagonalize the basis of integrals according to these cycles, we can easily represent every amplitude in any theory. And by choosing these cycles in a nice way, like for example, if you choose the spanning set that includes every UV divergent region, there's usually only one, and every different IR divergent region, then what you've done is just by diagonalizing against that basis, you have by construction ensured that there are individual integrals responsible for every infrared divergence specifically, and every other integral in the basis by construction, by diagonalization, is finite, is infrared finite, is free of all such divergences. And this is something you can do iteratively. We call it prescriptive unitarity because you write down a set of cuts and you engineer integrals to integrate to one on a given set of cycles. And it turns out that this strategy allows you to separate infrared and UV divergences, and it also allows you to separate out these different geometric structures that might appear. I don't have time to talk about these examples very well or in much detail, but a former student of mine and I showed that at least at two loops, we could fully stratify the integrands so that that this problem of having mixed polylogs and elliptic polylogs could be fully separated out, and that you have in this case, this integral here, we expect, or the diagonalized version of it, which is here, would be a pure polylog of weight 4, and these would be pure elliptic trilogarithms. But importantly, would fully separate out these separate geometries whenever they exist. So I wish I had more time to talk about it, but I realize I'm already substantially over time. So I'm going to kind of end on an optimistic big picture. That's not optimistic. It's just the big picture of this general program is that there's a virtuous cycle where somebody computes something very difficult, and that's the only way to get data. It's the only way to answer questions like this. And you stare at it, you think about it, you discover something nice. And then you can spend years trying to understand why and try to understand. But once you understand this, like for example, as soon as we understand these Calabi-Yau integrals, if we could understand them on the same level as what we understand polylogs today, I have no doubt that people like Lance would have been pushing it up to 8-loop order. I mean, this is the power that we have in the polylog sector is incredible, and but we're just missing the basic understanding outside of that category today. But because we're just talking about, we're not, the goal here is not a particular quantum field theory. It's really the general structure of Feynman integrals. The applications and the benefits go off to phenomenology, to many different categories, from particle physics to gravitational wave astronomy to early universe cosmology, and plenty of pure mathematics. So with that, thank you very much. Thank you for letting me go over a bit, and I'm happy to answer some more questions.
Thanks a lot, Jacob, for a very nice talk. Let's see if first Zoom audience have any questions.
Yeah, I have a question. Like, how far do you think you are from the goal of, say, working in the Hetoof paradigm of combining all sorts of Feynman diagrams in the strong coupling limit into a kind of a sheet, so that you get a string picture out of this business of perturbation theory? And
yeah, that's a great question. There was all orders. I'm not sure if we're getting rid of the Feynman expansion has been kind of a general theme here, but yeah, I'm not sure. There aren't that many all order statements that anybody's been able to make. So at least most of this talk, I was very fixed in perturbation theory at a given order. If you wanted to do the expansion in the 't Hooft coupling, or if you're looking at string amplitudes more specifically, there's the same functions arise there too. Been great work on string amplitudes by people like Oliver Schlotterer and Eric Doker and Michael Green, talking about some of these elliptic functions that appear there. And also you see hyperelliptics in perturbative string theory. But, getting rid of the Feynman expansion is an interesting, if you'd like something perturbative but without Feynman diagrams, I think the coolest new thing that I've seen is Nima had a paper. It's the first in a series of, I don't know how many papers, but about a couple of weeks ago, describing the combinatorics, very much isolated to scalar field theory, and mostly using examples in scalar field theory, where you get the exact same expansion as you would have from Feynman diagrams, but with this kind of strange combinatorial geometric picture behind it. And what's interesting about that, and what connects it to string theory, is that it does suggest there is a pathway which goes directly to classical string theory, or to familiar string theory. But there are also other kinds of deformations that also give you normal quantum field theory in the alpha prime expansion, but that generalize it somehow in a broader way. But I'm not on that paper, so I don't want to speak too much about that paper. I'm much more conservative. I'm really looking at the sum of Feynman diagrams at a given order of perturbation theory. And the 't Hooft expansion is not so important for me. In the sense that I'm just as happy to talk about non-planar things as planar things. Yeah. Usually I can go farther with planar. Yeah.
Right. When you were describing these graphs that may contract with these Calabi-Yaus and so on, were we always dealing with massless theories?
Or yeah, so yes, for those examples, my collaborators and I in these cases were really just looking for the simplest counterexamples we could find, or the simplest examples that had this. So all of these graphs are massless 5-4 theory in 4D. And also every integral on this page are finite integrals. So there's no regularization to worry about. There are definitely contributions to these amplitudes. In general, if you add masses to the integrals, it gets worse, and there's more Flabiau structure earlier. So the places where these like here in like these two loop integrals, nobody cares about a 10-point process in massless, involving gluons is so far outside of the LHC's concern that nobody cares. But where you do see the Flabiaus in phenomenology are where you have a top loop going through part of the graph, or top propagators. So you have a few masses and the rest is massless, and that allows you to start seeing this at 2 to 2 or 2 to 3. So you get if you have masses in the game, you see all of this happening earlier. And in general, there's more structure. But as far as we can tell, by more, I mean that if you have this integral and you add masses, what you find is that there's a lot of Flabiau threefolds. But there's still Flabiau threefolds. Yeah.
Thank you.
One question, somewhat broad and tangential. So one nice thing about so writing down analytic forms is that the analytic structure, right? So has anyone looked at how these amplitudes look at let's say on some other sheet? Maybe perhaps the structure simplifies. Maybe you find some zeros that are poles that you don't expect, singularities that you don't expect. For example, the bulk point singularity you see once you go to another sheet, right? I mean, I'm not sure whether there's any reason to expect such a thing, but I'm just wondering if there is any. Yeah.
So those are great questions, and I think they're all I'm not sure if I was about to say they're all being pursued, but I'm not sure if they're being pursued at that. I mean, I'm not sure. I think those are great questions. There are some things that I think have been answered for the Sunrise series, where we understand the structure more generally. But the picture that I think is going to happen, let me step forward in time or just make a prediction for how things are going to work here, is something that we're going to probably understand a lot better and a lot sooner than we understand these, before we give names to these Flabiau integrals, is the differential equations that they satisfy. And there's a nilpotency on these differential equations. There's a nice there's a nice structure there, and the analog of the symbol, which is like the locations of the iterated poles in a polylog, would be here. But anyway, the analog of like going to the next sheet is a little bit like taking a discontinuity, and the polylog is like cutting off part of the symbol. And I think that is all something that can be addressed on the level of the differential equations without understanding the names of these functions, or we can start understanding their analytic structure from the nice differential equations that they satisfy. But outside of this example and this series, I don't think anybody really understands the differential equations very well.
Some sort of Riemann-Hilbert type analysis. Yeah.
But it's something that is tractable today, whereas I don't think, there's a lot of other untractable directions of research, but that's definitely one that I think the right people can make good progress on today. Yeah. I'm not sure if I'm the right person for that, but there are people who exist who are better equipped at these differential equations methods. Yeah.
Okay. Thank you. More questions? If not, let's thank Jacob again for a wonderful talk.
Thank you so much. I appreciate it. And yeah, good to see you all. Good to see you, Edward.
Yeah.
Thank you.
Thank you.